Okay, so today we're going to be talking about Zeno's paradoxes. Okay, now I said the word paradoxes because if you're familiar, if you've heard the term Zeno's paradox, often it's talked about as though there's only one. But in actuality, there's 9 surviving versions, probably more. But they all say about the same thing. So the essential core of what the paradox is about is the same. So you could refer to it as his multiple paradoxes or a single paradox. You're talking about the same thing. There's not like a really fundamentally different paradox that somebody refers to. However, there are 2 that are the most notable versions, and those are listed as Achilles and the tortoise and the runner paradox. I'm going to list that now. I want you to know that there are 9 that do exist, but I'm going to focus specifically on these 2 because they're the ones that will come up the most if you ever discuss these. So some notable things about Zeno's paradoxes. It was the first use. Well, first, let me explain some background. Then we'll talk exactly what they are. What's very important about this and why we still talk about it today is it was the first use of reductio ad absurdum, which is a logical tool in which you have someone assent to premises that they agree to and show that through logical deduction there is a contradiction. And if you can show there's a contradiction, then you then can entail that one of the premises must be false. And that's really what Zeno was attempting to do. Now, this is often not understood about these paradoxes. The main thing that he showed, or at least he attempted to argue, was that motion was impossible. But that wasn't his goal, per se. That wasn't the end-all that he was going for. Really what he wanted to show was that plurality was impossible. That everything was essentially just one thing of matter. And that when we saw motion or we saw individual objects moving, that was merely an illusion. That did not exist. So now that we understand what he's trying to do is show that motion is impossible for a larger project, which is that there is no plurality, we can get into exactly what his paradoxes were. So, the most notable, or one of the most notable examples, is the tortoise and the Achilles version of this paradox. So I'm going to set it up for you. Now, in the lower right-hand corner, I've shown a mathematical breakdown of what this paradox is saying. You can ignore that for now. Let me first just set it up for you, and then I'll explain what's going on. So what we're told is, imagine that Achilles, who is a great athlete from Greek legend, is in a race with a tortoise. It's also not very fast or notable for its athletic abilities. So Achilles, recognizing this, says, "Okay, tortoise, you can get a head start. I will let you, let's say the race is maybe just 100 meters. I'll let you start at the 50-meter line. I know that I'm fast enough to be able to beat you." So the tortoise does. Now, the paradox, as Zeno argues it, is that if that is the case, that if Achilles is starting at the starting line and the tortoise is starting at the 50-meter line, that by the time the tortoise moves to the 51st meter line, Achilles, let's say, will have taken the 25 meters. He'll be at the 25-meter line. But by the time the tortoise makes to the 52nd, Achilles will have enclosed, again, half the distance between those two. He will enclose half the distance again. The paradox comes about in that every time Achilles closes half the distance, the tortoise will have then moved even more distance for him to close. So Zeno then argues that there will never be a point at which Achilles reaches the tortoise, because there will always be more distance for him to close between them. So from there, He then argues under the reductio that if that's the case, then one of the premises we're assenting to must be false, and that is that motion is actually occurring. Now, I want to direct your attention to the lower right-hand corner, because even though I will be explaining more about these paradoxes, they're not true. And that's what's really fascinating about this, is that it seems logically deductive that, what he's saying. But when we actually look at the development of these paradoxes and their history in math and philosophy, we're going to see that they're just not. So you can see we have Achilles down at 0, 0, and the tortoise, I think, is at 100. And so that's sort of, he has a head start. Now, the tortoise, we know, will move slower. So you can see the distance versus time axis, and I think it's at 1 minute. I'm not really sure exactly how this measures it. But at 1 minute, Achilles is still behind the tortoise. He has made it to the 100-meter mark, or the 100-meter mark. The tortoise is now at the 150-meter mark. At maybe it's minute 2, Achilles is at 150, the tortoise is now at 175. And you see that eventually it goes up, but notice that the second they get to, and I guess this is maybe like the 3rd minute mark, because of course, look, the time interval is shrinking between each distance. He meets him. He meets him at the 200-meter mark, and that is where he overtakes him. So now I'm going to try and explain the disconnect between what's going on when we think about this logically and what's going on in a more mathematical sense. But again, I will explain that. I first want to, if you didn't understand this iteration of the paradox, there's another one, the runner paradox. And so instead of a moving target, we just have one thing. So we have a runner, who is in this case a student. He's trying to get to spring break. But you notice every time, in order to get to the other side of, to spring break, he must go half the distance. And in order to make half the distance, he must then go half the distance of that. And in order to go half the distance of that, he must go half the distance of that, and so on and so on. There's an infinite amount of distances he must traverse. So, therefore, just as in the Achilles and the tortoise, motion is impossible. However, that is not the case. Zeno's paradox is predicated on bad math. The sum of an infinite series must be infinite. That was the assumption he's working under, and it's false. A single unit, like 1, the number, can be divided infinitely, but it's still only 1 unit. If you look at the lower right-hand corner, you can see that in action. We have 1 unit, and we can divide it in half, and fourth, and eighth, and notice that we can think of the half, the fourth, and the eighth as units in and of themselves, and we can sum them. And we can make that dot get infinitely closer to 1, but never touch 1. And we know that the sum of all of those units will equal 1. And that's what Zeno wasn't accounting for. That the sum of an infinite series can equal 1. And this is exactly what calculus was built on, was in some sense solving Zeno's paradox. Now, before I dissuade you of the importance of Zeno entirely, there are some really important metaphysical implications of Zeno-like paradoxes. And one is Thomson's lamp thought experiment. So what we're supposed to imagine is that there's a person holding a switch, and at time 0, the lamp is on, and at time 1, the lamp is off. And then every half distance, or every half second, well, it's not every half second, but every unit of time shrinks by a half. So 1.5, it's on, 1.75, it's off, 1.875, it's on, and we do that on and on and on and off, on and off, on and off, until we get to a full second has elapsed. Now we ask, is the lamp on or off? And nobody's really sure. Nobody knows exactly what the answer is. And there's very varying arguments as to whether or not the lamp is on or off, if this is even possible, what the metaphysical implications are. So Zeno does have a lot of import on today's and contemporary metaphysics. So I didn't want you to think that he was completely outdated. There's also some responses from science. Space is actually finite. You cannot divide space infinitely, and that unit is called a Planck length. It is the smallest amount of space that can exist. And to give you some idea of how big a Planck length is, that dot right under Planck length is halfway between the size of a Planck length and the size of the observable universe. So we're talking really, really small. There is no finite series in the first place, is one way we can think about it. Zeno was just sort of wrong on that front. Okay, now I'm going to end with a really stupid joke, but if you're familiar with Zeno's paradox, which you are now, you'll understand. An infinite number of mathematicians walk into a bar. The first goes up to the bartender and says, "I'll have a pint of lager, please." Each next one says, "I'll have half of what he's having." The bartender says, "You're all idiots," and pulls out 2 pints. Math jokes are just the worst.